All right, so here's the code that we wrote for the last lab where we were assigning the immediate value. Hopefully everyone is up to speed with that one. You might have bugs. There's a lot of data in here. Maybe you made a mistake in something. Might not be obvious in simulation yet. Might trip over it later. That can happen. Again, resolve the bugs when they pop up. So back to our slides. So we formed the immediate, right? So we've processed the immediate bits of the instruction, whichever type it is. Let's now look at the other fields of the instruction. So basically, all the other fields that we might want to extract from the instruction always come from the same place in the instruction. If you look at this table, RS2 is always these bits. RS1 is always these bits. RD is always these bits. Basically, whatever fields among RS1, RS2, RD are needed, they're there. The bits that are left over are used for immediate bits. So the R type, which uses both RS1, RS2, and RD, has no immediate. It uses the available, the remaining bits for this funct 7, which helps narrow down, well, actually it's not even really used, but it's kind of available to use to specify more of a breakdown of the actual instruction that's being executed or to be executed. The other instructions maybe don't use both source 1 and source 2 or don't use the destination, so there are more bits available for immediate. So for this lab, we're going to extract the other fields. Since they always come from the same bits, it's really just a straightforward assignment. So here I've started you off with RS2. RS2, the register file is 32 entries, so it's a 5-bit field for the register index to index into the 32 entries. So RS2 is a 5-bit value, and it comes from bits 24 down to 20. Okay, so it's simple assignment. And for some instruction types, that's going to be valid. For other instruction types, it's not going to be valid. No need to worry about that at the moment. If we need to have it, that's where it comes from always. So direct assignment, same thing for the others. So you'll do funct 3, RS1, RS2, RD, and opcode. Func 7 we don't actually need. So yeah, don't bother. Put up your green card for me. What's the difference? Yeah, let me talk about that up here. Yeah, so in case it's confusing to folks, there are two tables, right? One that maps out the bits of the instruction. So 31 down to 0. And another table that maps out the type, the immediate. I think maybe maybe I drew this earlier when we were talking about the going through the decode cards, right? This is a mapping of the instruction bits. This is a mapping of the immediate values bits. So, you know, maybe some of these immediate, maybe we're forming the immediate by grabbing some of these upper bits, and they map to the immediate in this field. So you can kind of, when you're talking about the immediate, you can look at the instruction and say where are those immediate bits going to in the immediate field, or you can look at the immediate field and say where are the instruction bits, where are the immediate bits coming from in the instruction. They're just inverse mappings of each other, right? You're mapping bits of the instruction to the bits of the immediate field, and you can represent the table either way, with respect to the immediate bits or with respect to the instruction bits. Right, all the different instruction types have each of the fields in the same spot. So regardless of the instruction type, you're always getting the field from the same bits. Right. Right. So for those instructions that don't use a particular field, the logic that's evaluating those instructions had better not use that field. So in that case, the value is a don't care. Right. So we'll just do the direct assignment. Mm-hmm. The compiler knows what instructions it can generate and compose into the program, right, into the assembly code. It knows which instructions use which type. It knows how to pack the bits appropriately, doing all the things that we're doing here. Right. 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 So the instructions that the compiler is generating or the assembler is generating, either way. Um, uh, sure. Right. You're never trying to generate an instruction that requires both fields. It's one type or the other. Right? The compiler knows what instructions it has available to use. It knows which one it's choosing. It knows which fields they have. It knows how to pack those fields. Show me your green cards if you're ready. Okay, I think most people are ready. I've typed my code here. Hopefully I got all the bits right. So now let's consider the fact that these fields aren't valid in all cases, right? When are they valid? That's validity. Kind of click a circuit in your mind. Let's use the when construct here. So let's convey explicitly when these fields have meaning and when they don't. So let's determine the signal that tells us when they're valid, and then apply that signal as a valid condition. So for each field, RS2, for example, the RS2 field is going to be valid for R-type, S-type, B-type instructions. So let's assign this signal. If it's R-type, S-type, or B-type, then RS2 is valid, and then use that as a when condition. When RS2 is valid, this assignment has meaning. Right, and then you can continue for the other fields. Yeah, and then, of course, indent the statements that you just created so they're under the when condition. Mm-hmm. There is. Yeah, you can search for TL-Verilog mode. You also can use MakerChip in a mode where you're using an external editor, right? So if you wanted to use VS Code, you can edit your code in VS Code, and then under Project, Connect File. And then when you edit externally, when you compile in here, it'll grab the current version of your code and compile that. Are we good? Ah, yeah. So the logic that we're doing now is to reflect when these fields have meaning, right? What was the question? Well, I mean, this has nothing to do with the compiler, right? The compiler, again, the compiler is aware of the instructions that it has available and is choosing amongst them. It knows what instruction it's choosing, it knows what the type is, so it knows how to pack the bits accordingly. And there are no instructions that are using both one of these fields as well as the immediate bits that would otherwise be used in that field. Right? The compiler has all the information that it knows that it needs to know how to use these bits. Okay, so next lab. Okay, so we've decoded the instruction type, we've decoded its fields. Now we're going to decode to the level of the individual instruction, right? Essentially breaking it down by its mnemonic. We're going to start, so we're going through the whole CPU core to implement the functionality that's needed to execute our test program. We're going to implement this subset core, see our program running. We'll go back later and add the other instructions back in and all the details. The instructions that we need for our test program are add I, add, and branch less than, I think. Since we're implementing that branch, we'll just go ahead and implement all the branches. So we'll do all the branches and add I. So let's see. So So in order to decode which instruction we're talking about, we need the opcode field and we need the funct3 field. Sometimes we need this instruction bit 30. So to make the decode code a little bit simpler, let's extract those bits and pack them into a single vector. So we'll define this decode bits field that's 11 bits. That's the concatenation of these three. And then for each type, similar to what we did with, sorry, not each type, for each instruction, similar to what we did for instruction type, we'll have a signal, is this instruction mnemonic, if the decode bits match a particular pattern, right? So for BEQ, that pattern is here, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1. So if our decode bits match that pattern, we're branch equal. Okay, and then all the other, however many, 8 or so instructions look the same. Again, if you copy this, sorry, again, if you copied this, you got the wrong tick. Just fix that. By the way, I forgot to mention this underscore here in the binary number. Verilog allows you to freely place underscores in numbers. They're ignored. It's just a way to kind of delineate fields. So for me, this is delineating the func3 bits from the opcode bits. Just helps to make it more readable. So I think once you're done that, you should see in the visualization that the decoder is able to determine what the instructions are. So for example, here I'm going to add instruction. I can see that in the decoder. Right. The visualization here is triggered by all these signals that we just created, the ISB, Q, ISB, NE. So if I play this forward, I should see the correct interpretation of the mnemonics. Okay, so you can give yourself a quick sanity check on those just to make sure all the mnemonics pop up correctly. So, yeah, as we're in stage 1 of the pipeline now. So what we're implementing now, everything is in stage 1. We're just going to do everything in a single cycle. In that one cycle, we're going to process the entire instruction, all this, decode, read the register file, go through the ALU to compute the result, write the result, all in one stage. After we do this and get it functioning, then we'll stretch it out and implement a multi-stage pipeline. All right, so again, take a break for a second. I'll introduce the next lab. So that's it for our decoder, at least for the subset CPU, right? We've characterized our instructions. We know what the instructions are. We know what its fields are. Now we need to access the register file. So part of the sort of motivation behind the instruction set architecture is to define the instructions in a way that they can be executed efficiently. You saw that RISC-V chose to always put the RS1, RS2 fields in the same place. That means coming out of the instruction memory, those instruction bits with the register file index don't have to go through any logic to get to the register file. They're just direct hookup straight from the instruction memory straight to the indices of the register file. That helps to streamline the CPU, right? This is a critical path that we're looking at all the way from PC through fetch, decode, register access at ALU. By keeping the RS1 and RS2 fields in the same place for every instruction, we help to streamline the logic and kind of get rid of the decode logic from the critical path. Some of the other aspects of decode, for example, the immediate fields, forming the immediate, that's not on the critical path. We don't need the immediate field for most instructions until after we've read the register file. So that's why the immediate bits are that's one reason anyway, that the immediate bits are more scattered. We can afford a little bit of delay in that logic to figure out what the immediate bits are. Okay, so the register read, we're going to do the register file similar to the way we did the instruction memory. It's an array structure. I've given you that component. We'll just uncomment it and drop it down. So you can uncomment this R5RF macro. The arguments here, the @1 and the @1, this happens to be this pipeline stage at which we're going to read, and the pipeline stage at which the data is going to come out of the register file. For us, we're doing a single stage implementation, same stage. So the circled inputs here are the ones that relate to read. We have we need to support 2 operands, so 2 reads. So this would be referred to as a 2 read, 1 write register file. We're producing 1 output value that needs to write every cycle, so 1 write. So a 2 read, 1 write register file. each read has an enable and an index. So this lab is hooking up these inputs. Yeah, so in this case, when we leave these dangling, they're going to take on default values the way the template is set up. So again, this lab is to just make the connections. When you uncomment this, you get signals that have this name, these names, and you just need to hook those up appropriately to the corresponding signals in your logic. So these are coming from the decoder, right? So what's the enable for the first port? That's going to be if there is a source 1 register. The enable for the second port, if there is a source 2 register. The index of the first read, the register file, the register index for this first source, so RS1. And likewise for the second, RS2, the index of that register, that's the address that we want to look up in the register file. So hook these 4 up, and you can run simulation, and you might see a little more behavior now in the visualization. Is that true? Probably not yet. All right. Yeah, I mean, once you understand the macro, logic for the array will exist. You can see that. I'll go ahead and uncomment it. So this is the RF macro. So similar to before, we should see all the dangle warnings. If the visualization doesn't hide them, it might. But you can see in the diagram. So now we have this XReg 15 to 0. So we're actually using 16 registers instead of the full 32. This is so we can actually fit better on the FPGA. But let's see. So we're seeing these signals driving the register file that aren't driven, right? So all of these register file inputs are currently dangling. So you can kind of see that here. And then similar for the output. So here's my read data. No, these are only inputs. Let's see, what is this? So that's the read index affecting the logic expression for read data. Yeah. Source register. So respond to one. This instruction to okay. Okay, so the enable is hooked up to the corresponding valid. And read index. Is RS1. So I don't remember exactly how the visualization is hooked up, but it looks like we're seeing register indices. So X13, X11. So that was, or X10, that was probably showing before. So probably the next change we'll see in the visualization is when we hook up the data, the output data from the register file. So let's go to the next lab. Anybody need me to slow down? So the hookup here, right, the source 1 register is going to use port 1 of the register file, the read port 1. So the read enable for that is going to be if there is a source 1 register in this instruction, we need to read. If there's a source 2 register, we need to read in port 2. The indices that we're going to read are the fields that we extracted from the instruction, the RS1 and RS2. So now we'll hook up the outputs, the read data from the register file, right? This is the corresponding register values for source 1 and source 2. We're going to feed those into the arithmetic logic unit to perform the calculation on those two values, right? So I guess we have to refer back here. So the register file output is RF read data 1 and 2. And we want to hook those up to the source 1 value, source 2 value, just to give them names that are appropriate in the context of a CPU. Okay. So pretty straightforward. We can do that one together. It's part of RF read, I guess. So we're assigning source 1 value, which is 32 bits, to be straight from the data from the register file, port 1. So that's going to be RF read data 1, I think. Let's just check that. RF read data 1. All right, that's a value. So you'll notice that in the visualization, the register file is initialized with values where each value matches the index, right? 0, 1, 2, 3, 4, 5. Typically, you would reset a register file to have 0 values. Here, I've reset the register file to have those values that correspond to the index. It just makes it a little bit easier in the simulation to verify that which value you're reading out of the register file. So now that we are actually reading data from the register file, we'll see the data that's being read in the decode logic here, right? So this instruction is reading from X10 and X0. X10 grabs the value from the register file, which is 10. X0 grabs the hardwired 0 value. So you can verify the behavior in your simulation to make sure that the registers that you're reading, you're actually getting those values in the decode logic here. Right? So this value, for example, the 10, that's coming directly from the signal that we just hooked up, the source 1 value. look at the ALU and then we'll take a break. So we've hooked up the signals that'll be the inputs to our ALU, the source 1 value and source 2 value. Our ALU needs to perform the requested operation. For our subset of instructions, we need add-I, and also the branch instruction. The branch instruction is not performing any computation using the ALU, at least not the way we're coding this. So the only instructions we need to worry about are add and add-I. So there's not really much to do here after I get you started. So the ALU is assigning a result. We'll call that result. It's 32 bits. And, you know, again, like I said, we're going to build this CPU out of muxes. The ALU is going to perform a different operation for every possible arithmetic instruction. So first for add-I, right? If this instruction is an add-I, the result should be the source 1 register value plus the immediate value. That's the definition of the behavior of add-I. It's adding the source to the immediate. And then you can fill in the only one left would be add. So if this is an add, the definition of the behavior of the add is to add the two source registers together. Okay, so pretty straightforward. So code that up, take a look at the, let's see, what are you going to see in the visualization? I mean, you can assign to anything. Again, this is just a default assignment that we should never be reading. But at this point, you should see in the visualization the output value here. Right. Yeah, you can have multi-driven buses in Verilog that default to a Z value, and you know you should have one and only one driver of that bus, at most one driver. If there are no drivers, it would be hold the Z value. We tend, I mean, regardless of Verilog or TL-Verilog, we tend not to use that design style anymore because it's hard for the tools to analyze. But you know, in the rare cases when you do want that structure, you can still use the Verilog assignment constructs in TL-Verilog. We're going to avoid that. But yeah, I was saying the result that we're assigning here is reflected in the visualization here in the decode block. So you should see meaningful results now calculated for add and add-I. Now that we have our result hooked up, you should see, as I said in the visualization, adding 10 plus 0, we get 10. Adding 13 and 14, we get 27. So next is to hook up register file write, right? We've instantiated our register file, but the write control signals are still dangling. So let's hook up the write inputs. So we have a, so the register file, we're sending in 2 reads to do. We go through the ALU completes, produces a result, and that result needs to write. So we have inputs that enable the write if the instruction has a destination register. And we have the destination register index from the instruction to use as the write index. And then we need to provide the data that we're going to write, which of course is the result from the ALU, right? So let's hook up these 3 appropriately, right? So again, when we instantiated that macro for the register file, that gave us these 3 dangling inputs, which we need to assign. So create the assignment statements for these 3. This is provided, this is what the macro, so the macro is instantiating the logic of the register file. That register file logic is consuming these 3 signals, which currently are unassigned. Yeah, so the enable needs to always be a 0 or a 1, right? And the index and data need to be valid when we are writing. Right, so so the write enable for the register file, when the instruction has a destination register, it should be writing to the register file. So the write enable is RD valid. You've already coded RD valid, right? So you just need to hook that up and create the assignment of, hook it up by creating the assignment for RF write enable. Okay, so you're coming up with assignments for these 3. Last one here, step 3. So after you've done that hookup and checked out the simulation, we'll add in the wrinkle that in RISC-V, register 0 is a hard-coded 0 value. So we've instantiated a register file that actually contains R0. We will force it to 0 by never writing it. It's going to default to a 0 value. So as long as we never write R0, we'll always get a 0 when we read. So when you write, if the RD is 0, you need to disable the write enable, right, to prevent writes to R0. So that probably, Okay, so for this lab, just to walk through it, I know some of you are still working on debugging various issues. That's fine, but to complete this lab, right, we're hooking up these three inputs to the register file. So we need to enable the write when, actually I put this comment in the wrong place. We need to enable the write when the destination register is valid for this instruction. The index that we need to write is given by the RD field, destination register field of the instruction. And the data that we need to write is what's coming out of the arithmetic logic unit. I did not yet do step 3. Okay, so step 3 is to deal with the fact that the X0 register is an always 0 register. And we're going to accomplish that by not writing to R0 ever, or X0 ever. So we want to do the write if RD is valid and it's not 0. So RD is not equal to, will be explicit, sorry, 5-bit 0. Makes sense? Okay, so if you do have bugs and you're still working through bugs, you know, don't worry about it at the moment. You can get back to it. Let's see what's next here. So just an aside, right? For the register files and a register file and memory, we just plopped down a module and didn't worry about what was inside. Not critical for anything, but for the curious, I know a lot of you have been asking questions about it. What's inside the register file? So this is a logical view of what a register file or what a memory is doing. Logically, we have the let's say register file, right, has 32 entries. Our register file actually has 16 entries, but all the hookup is with bit widths that reflect a register file that would have 32. So assuming we have 32 entries, right, each one of these blue boxes represents a value in the register file, and we would have 32 of those. So we have 32 values in the register file. Those values are represented by the crossing of the clock boundary here. Let me get my pointer. This, right, is a flip-flop, or at least a state element. The reality is when you implement the register file, you use different technology to implement that than flip-flops, but we're just looking at a logical view here, so let's just say flip-flop. So this is our flip-flop that's holding on to register, the register value at index 1. And we have 32 of those, so here's index 1, index 0. So 0, 1, 2, etc., down to 31. For each of those values, right, we need to, what should we look at first? If the right index is my index, so this comparison is with my index, so for index 0, this is the right index equal to 0? And the write is enabled, then I want to write the value that's sent in, the write data. Okay, so every entry is going to have the same logic for their own special index, and one of them is going to match and write if we're doing a write. We also want to reset the whole structure to 0, so we'll have a reset selecting 0. And if we're not in reset and we're not doing a write, we want to retain the value. So as always in TL-Verilog, we'll think of that as an explicit recirculation through a mux. So that's the write operation that happens in each value, and then the read operation is a big multiplexer across all of the entries in the structure, right? Selected by the write index. So this is an encoded select amongst all the values in the register file. Read the data. The read enable can factor into the select here, or maybe force a 0 value on the read data. really doesn't matter. The read enable is just a power savings, right? If you're not trying to read data, you better not be trying to consume whatever is randomly coming out. So it doesn't functionally really matter what you do with read enable. If you're trying to read and write at the same time? Yeah, so there can be constraints based on the physical implementation of the register. That might not be a permitted operation, but logically, the way I've drawn it here at least, if you perform a write and simultaneously perform a read, you should get the value that you wrote, right? That would be the write data is coming through as the read enable is going through, and the data goes through this mux, it goes through this flip-flop, it gets selected, it reads out. So what's more interesting to look at is kind of the TL-Verilog view of the read and write operation in the context of a pipeline. So in this view, we're looking at the read and write operations coming in simultaneously at the same pipeline stage. The reality is, let me think. I'm just trying to think what I actually have depicted here. Okay, so if we have an instruction that is doing a read of source operands and it's also doing a write, right? What I just talked through, if we're doing a simultaneous read and write, we get that value. That's not what we want in our register file for an instruction. If the instruction is doing both a read and a write, we want the read to get the value from the previous operation. Okay, so the value that we read should be coming from a stage ahead in the pipeline, right? So this pipeline has instructions marching through it, instruction, instruction, instruction. If this instruction is doing a read, it's the data as updated by this instruction that we should be reading. So when we put all of this in the context of a pipeline, as it would be utilized by the CPU, we want the data that's written to be in stage 2 for the read in stage 1. So this is the data in the register file. The read functionality is associated with, so let's call these instructions A and B, right? We're looking at the read that B is doing. The data that B wants to see is the data that was written by B. So this crossing of the pipeline represents the state of the register file, all the contents. And, we're reading it around like this. This is the logical view of what's happening, right? Physically, we're not going to route wires very far. We want that to all be local. But logically, it's the data written by B that we want to read by A. And, so where I showed, the logic all kind of lined up in a natural way, when we put the read and write operation and associate them with the instructions that are doing the read and doing the write, you kind of lay the logic out this way, right? The read operation, which is performed by these muxes associated with instruction B here, should be in stage 1. The write operation, the logic that we looked at for the write here in the blue boxes, we're deciding what to write in stage 1, capturing that into stage 2 so that it's available for the next instruction going through. Okay, so normally when you see a logic diagram of a CPU, folks are going to draw a register file as one box. That's one thing. Physically, it's a structure, it's a register file, it supports a read and it supports a write, and they'll hook up the wires. Mapping it out this way, it's, you know, it looks a little bit uglier as a logic diagram, but it's organized very clearly that what's being done at each stage by a particular instruction. Okay. So it's very clear when you map it out this way that the data that you're reading is the data that was updated by the instruction before because of this one cycle loop. So it can be a little confusing at first, but when you learn to think about things this way and you map it out this way, it can avoid a lot of the careless mistakes with timing where you know you're inadvertently reading the data you just wrote or something like that. So not too crazy and not too important for the simple CPU, but if you're designing an Intel class CPU, the picture gets exponentially more complex, and if you don't have a clear thought process and a framework for thinking about time, you can easily make a lot of bugs that can be hard to debug. Okay, so again, this all is sort of an aside to help with the thought process, but as far as the, you know, the course content, we just give you the register files and you don't really have to think about it. Okay, if there are any questions, I can field them. Okay, so just something to get the gears turning. So the next piece of logic that we need to worry about is branches. So let's take a look. I suppose this should be a white box. We haven't implemented that yet. But let's take a look at the logic that's computing whether we need to take a branch or not. So we've already decoded the branch instructions to know whether we are, you know, BEQ, BNE, etc. We haven't evaluated the condition that tells us whether we need to branch or not. These are the conditions for each of the instructions. So BEQ, you're branching if the two sources are equal. BNE, branch if not equal. Branch if they're not equal. Branch if less than, surprisingly. You branch if they're less than. This is a signed less than comparison. We're doing the comparison in an unsigned way. The correction for that to make it signed happens to be this. It's kind of an XOR on the top bits. Branch if greater than is similar, and these are unsigned comparisons, so they don't have the complexity of dealing with the signed bit. So BLT branch less than unsigned, you're going to take the branch if the source 1 is less than source 2. Okay, so the ISA defines these 6. So what we're assigning here is this taken branch pipe signal. And of course, as I keep saying, it's all muxes. So depending on the type of branch, BEQ, BNE, you'll use a different comparison operation to determine taken branch, right? So if this is a BEQ, then you're taken branch if the two sources are equal. Similar for the remaining. So, so the way I'm suggesting is, well, not just a suggestion, this is required. So taken branch should be an accurate reflection of we are a branch and we're taken, right? So if we have a non-branch instruction, we want taken branch to be 0. So you can condition it on, am I this branch, am I this branch, am I this branch? The default then is I'm not a branch, so we're not a taken branch, so we should return 0. So the default case should be 0. Any questions? And if you're still working on old exercises, that's fine. You can continue with those. So what happened over here? So after this lab, we have, I think, just 2 more labs to complete the subset CPU. I say we just power through. It's almost 5:30, but we'll just go probably a little bit beyond 5:30. I think it's worth finishing up to get to a nice checkpoint. How's everybody doing? Green cards? I see several lime green cards. They're like a little green, a little yellow. Basically done, but still debugging some little oddness. That's fine. Yeah. So Okay, so one of the students just now was noting that I'm doing the take and branch calculation before I do the register read. It's not that I'm doing it before the register read, it's just that that's the way I ordered my code. The code order doesn't matter. The code is declarative. I'm just declaring the existence of the logic. But sure, I kind of agree. Since we're doing the RF read first, maybe the branch code should be down here. But it makes no difference. Any other questions before we do the next lab? All right, so for this lab, we determined whether we should take the branch. We haven't actually acted on that, and we don't yet know where to branch to. So let's see what's next. So next is to figure out the target of the branch. The target of the branch is defined as the program counter plus the immediate. Right, the immediate is an offset from the current PC for the branch. Okay, so step 1 is to compute the branch target. Step 2 is to actually use that branch target and the fact that we are or are not taken. So if we are a taken branch, we need to update the PC to this branch target. So this becomes another input to our PC mux enabled by taken branch. Right? So we've defined taken branch to mean we have a branch instruction, and I don't think we have a valid signal at this point. Okay, I guess we did it right. We have a taken branch instruction, and the condition is true, so we should branch. So taken branch means we should branch. That's our select now for the PC mux to select this branch target PC. And you can tell from the logic diagram the way I drew it, right? We're taking the decision made by this instruction in stage 1 and applying that to the PC of the instruction after, right? So if this instruction in stage 1 is a branch, the instruction in stage 0's PC should be the branch target of this guy. Okay, so make sure you're hooking this up with the right relationship, timing relationship. That's it. Check your behavior, debug it. After this is hooked up, your code should actually be taking the branch. Right? I wanted to note, somebody was observing also that the visualization in the default template is, I didn't realize this, is configured to visualize what's happening to the instruction that's in stage 4 of the pipeline. Let me see if that's the case here in my code. Yeah. So this viz macro is instantiated with a parameter at 4. That's causing the visualization to represent the instruction at stage 4. Right? So the visualization is actually causing this whole pipeline to extend out here, and it's representing that. So when you're looking at your visualization and your waveforms, just realize that the cursor, the white cursor, is telling you the time of the visualization. That reflects at 4, whereas the signals that you're looking at are a different time. So you have to adjust for that. You can also, at this point, it's safe to change this at 4 to an at 1 should be fine, I think. But just realize we have to change it to 4 when we stretch the pipeline out. Okay, so should be 1 less than 10. I'll walk this through up here. So my target PC is the PC plus the immediate. And then I need to update the PC mux way up at the top such that the next PC for this instruction, if this instruction is a taken branch, will be its target. So if the previous instruction was a taken branch, that's right, then I want to use the previous instructions branch target PC. And with those changes, hopefully my CPU is now taking branches. Moment of truth, it took a branch. So if I let this run, we'll see if it's actually computing correct values. Okay, so here we have 10 bowling pins. Now we have 15 pool balls. Should go to 21. Seems to be summing numbers correctly. And let's see if my CPU stops correctly. This should be the last iteration. It should fall through, which it does. So I think the next one should be the last one for our CPU. Yeah. So this last one is pretty quick. So I think most of you have your CPUs working, at least many of you. Working at this point means that you're getting that 45 value and then your code just falls off the edge of the earth. So let's put a proper test bench in place to check that your program passed. So we're just going to monitor the value of x10, which is where we write the final result, and see if it's the value that we expect. So, just type this line, right? So what this line is saying is we pass if the value in the x10 register, and this is syntax that I haven't really explained, but this is reaching from the CPU pipeline into the X register, index 10, so the value in register X10, and checking that it is the sum of 1 through 9. We're looking ahead in this pipeline 5 cycles just to delay the stop of the program. It just lets the program run for another 5 cycles. So yeah, just add that line, and your log, once you add that line, should properly report that your test passed if it did indeed produce a value of 45. So that's the last one for today. When we come back tomorrow, and I'll save a recap for tomorrow since we're over time. But when we come back tomorrow, we're going to play around with cardboard some more. And start thinking about how we stretch this pipeline out into multiple cycles so that we can implement a higher performance core. Okay, so tomorrow is going to be all about pipelining.